There's a star system 4.37 light-years from Earth. That sounds like an enormous distance, and in any practical, human sense, it absolutely is. But in the cosmic scale of a galaxy that stretches 100,000 light-years from one edge to the other, Alpha Centauri is basically our next-door neighbor. It's so close that on a clear night in the southern hemisphere, you can look up and see it with the naked eye. A faint golden dot nestled near the Southern Cross, quietly burning in the dark. For decades, we've pointed our best telescopes at it. We've listened for radio signals from its direction. We've debated whether planets orbit its stars. We've even dreamed seriously, mathematically, expensively dreamed about sending tiny robotic spacecraft to fly past it within our lifetimes. And now, the James Webb Space Telescope, the most powerful observatory humanity has ever built, has turned its golden eye toward that system. And what it found is not what anyone expected. Not the planets, not the stars, not the distances. Something stranger. Something that, depending on who you ask, either deepens one of the greatest mysteries in modern astronomy or quietly, almost gently, suggests that the universe is far more alive with possibility than we ever dared to believe. So let's talk about Alpha Centauri. Let's talk about what Webb saw. And let's talk about why, after centuries of staring at our closest stellar neighbor, we're only now beginning to understand what's actually sitting there, 4 light-years away, waiting. To understand why this matters, you need to know 2 things. You need to know what James Webb is, and you need to know what Alpha Centauri is, because when those 2 names appear in the same sentence, something shifts. Something in your brain registers that this is not routine science. This is the most powerful instrument in human history, pointing itself at the most important destination in the night sky. James Webb launched on Christmas Day, 2021. It took 30 years, $10 billion, and the coordinated effort of thousands of scientists and engineers across multiple continents to build it. Its primary mirror is 6.5 meters across, composed of 18 hexagonal gold-plated beryllium segments that unfold in space like a flower blooming in slow motion. It doesn't orbit Earth the way the Hubble does. Instead, it sits nearly 1.5 million miles away at a gravitationally stable point called Lagrange Point 2, perpetually in Earth's shadow, kept at temperatures so cold they approach absolute zero. Why? Because Webb sees in infrared light heat radiation, and to detect the faint warmth of distant objects, the telescope itself must be almost perfectly cold. Webb wasn't designed to be romantic. It was designed to be precise, to see through dust clouds that blocked Hubble's vision, to peer at galaxies forming at the dawn of time, to analyze the atmospheres of planets around distant stars. It was, in every engineering sense, built to answer the questions we've been asking since the first humans looked up and wondered what was out there. Alpha Centauri is our closest answer. It's not a single star. It's actually a triple system, a gravitational family living in close proximity. Alpha Centauri A and Alpha Centauri B are 2 stars that orbit each other in a slow 7-9-year waltz, so similar to our own sun that if you squinted at them from the right angle, you might momentarily mistake them for home, a little further away, gravitationally bound but orbiting the pair from a vast distance is Proxima Centauri, a small, dim, red dwarf star. And Proxima has a planet, a rocky world called Proxima b, sitting right in the zone where liquid water could theoretically exist. 4 light-years away, a potentially habitable world, and now Webb is looking directly at it. If that doesn't make the hair on the back of your neck stand up, I don't know what will. Before we go any further, if you're the kind of person who gets genuinely excited about space science, about the real discoveries that are quietly reshaping our understanding of the cosmos, then hit that subscribe button and leave a like on this video. It genuinely helps this channel reach more people who care about this stuff. And trust me, you don't want to miss what's coming up in this story. We live in a galaxy with somewhere between 200 billion and 400 billion stars. When astronomers talk about the search for life beyond Earth, they typically gesture at the Milky Way as a vast, almost incomprehensible canvas of possibility. And they're right to do so. The numbers are staggering. The chances, statistically, seem almost overwhelmingly good that somewhere in that enormous crowd of stellar fires, something is alive, thinking, looking back. But here's the uncomfortable truth that doesn't get said enough. Most of those stars are so far away that they might as well be fictional. Even our fastest spacecraft, moving at roughly 35,000 miles per hour, would take tens of thousands of years to reach the nearest ones. The galaxy is real. The possibility is real. But the reach, the actual physical reach, is essentially zero. Alpha Centauri changes that calculation. Not completely, not practically, not yet. But philosophically, mathematically, and in terms of scientific scrutiny, it exists in a different category than every other star system beyond our own. It is close enough that the light you see from it tonight left only 4.37 years ago. It is close enough that some serious, credentialed, peer-reviewed proposals have been made for sending actual probes there within a human lifetime. The Breakthrough Starshot Initiative, backed by Stephen Hawking before his death and funded by tech billionaire Yuri Milner, proposed accelerating gram-scale laser-sail spacecraft to roughly 20% the speed of light, using an enormous ground-based laser array. At that speed, they could reach Alpha Centauri in about 20 years. 20 years, not 20,000, not 20 million, 20. That is the difference Alpha Centauri makes. It transforms interstellar travel from pure mythology into something that sits precariously but genuinely on the edge of engineering possibility. And that means anything we learn about that system, any planet, any signal, any anomaly, carries a weight that observations of more distant stars simply cannot. There's also something deeply human about it. Alpha Centauri has been in our sky for as long as humans have had eyes to see it. Ancient Polynesian navigators used it. It appears in the mythology of various Southern Hemisphere cultures. It was cataloged in detail as early as the 17th century. For a very long time, it was simply a bright star, beautiful, fixed, distant, in the way that all stars are distant, and therefore, in the casual human sense, irrelevant to daily life. But then, we started finding planets around other stars, thousands of them, and the question that had always been quietly lurking in the background suddenly pushed its way to the front of the room. If planets are everywhere, what about the planets around our nearest neighbors? The answer, as it turned out, was complicated and fascinating, and still, even now, beautifully unresolved. There's one more dimension to Alpha Centauri's importance that rarely gets enough airtime, and it has to do with something called the Fermi paradox. In 1950, the physicist Enrico Fermi sat down for lunch with a group of colleagues and, in the middle of a conversation about extraterrestrial life, asked a question that has haunted physics and philosophy ever since. If intelligent life is common in the universe, where is everybody? The galaxy is old enough, and interstellar travel is theoretically possible enough that a sufficiently advanced civilization could have colonized the entire Milky Way many times over in the billions of years since the first stars formed. And yet, we see no evidence of this. No signals. No megastructures. No visitors. Nothing. Alpha Centauri sits at the heart of that paradox in a specific way. If we ever do develop interstellar capability, if humanity ever builds those laser sail probes or something even more ambitious, Alpha Centauri is the first place we go. It is the first rung on the ladder. And by that same logic, if any civilization anywhere in our stellar neighborhood ever developed such capability, they would have passed through this system. They might have stopped here. They might still be here, in some form we haven't looked for yet, or with a presence so subtle that our current instruments are blind to it. Webb won't resolve the Fermi paradox. That's not what it's for. But it is, for the first time, giving us the kind of detailed infrared portrait of this system that would allow anomalies, things that don't fit natural explanations, to surface if they're there. And that alone makes what Webb is doing at Alpha Centauri one of the most quietly consequential scientific activities in human history. Here's where the story gets interesting in a way that most science coverage tends to skip over, because it's not the kind of narrative that fits neatly into a headline. The truth is that for a long time, astronomers had deeply conflicting opinions about whether Alpha Centauri could even host planets at all. The problem is the system's complexity. Alpha Centauri A and B orbit each other at an average distance of roughly 23 astronomical units, about the same as the distance between the Sun and Uranus. That's actually pretty far by human standards, but in stellar terms, it's close enough that the gravitational interaction between the two stars creates a chaotic, churning environment in the inner regions of their orbits. Planetary formation theory, the models that describe how dust and gas coalesce into rocky worlds and gas giants, had long suggested that this kind of binary gravitational environment would make stable planetary orbits difficult to maintain. The stars would yank developing protoplanets out of their orbits, disrupt the accretion process, prevent anything stable from forming in the habitable zones. That was the conventional wisdom for a long time. Alpha Centauri A and B, probably no planets, too messy, too gravitationally turbulent. And then, in 2012, a team of astronomers announced that they had detected a planet around Alpha Centauri B using the radial velocity method, a technique that measures the tiny wobble a planet's gravity induces in its host star. The announcement made headlines worldwide. A planet right next door. The science world briefly erupted with excitement. Then, 2 years later, a different analysis of the same data concluded that the signal was likely an artifact, a ghost, in the data created by the way the measurements were processed, not a planet. A mathematical echo. The excitement deflated almost as suddenly as it had inflated. Then came Proxima b. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri, the small red dwarf companion to A and B, using the radial velocity method. This one seemed to hold up under scrutiny. Proxima b appeared to be a rocky world, probably somewhat larger than Earth, orbiting its star in just 11 days. And because Proxima is so dim, that close orbit still puts Proxima b within the habitable zone, the range of distances where liquid water could theoretically exist on a planet's surface. But there were enormous caveats. Proxima Centauri is a flare star. It erupts with intense ultraviolet and X-ray radiation in powerful, irregular bursts that could strip the atmosphere from any planet nearby. Whether Proxima b actually has an atmosphere, whether it could hold on to one in that environment, was and remains a genuinely open question. So what were scientists expecting when Webb turned its attention to this system? They were expecting to learn more about what we already knew was probably there. Clarification, refinement, better data on Proxima b perhaps, insights into the stellar activity of these three stars, more confident constraints on the question of whether any of them could harbor life. What they were not necessarily expecting was something genuinely new, something that didn't fit neatly into the existing models, something that made scientists pause, compare notes, run the analysis again, and then pause once more. Here's a puzzle that sounds like it shouldn't be a puzzle. Why is it hard to study stars that are very close to us? Shouldn't proximity make things easier? If Alpha Centauri is only 4 light-years away, shouldn't our telescopes be able to see it in incredible detail? The answer is complicated, and it gets to the heart of something genuinely counterintuitive about modern astronomy. Webb is optimized for looking at things that are very far away and very faint. It was built to detect light from galaxies that formed 13 billion years ago. Light so ancient and so stretched by the expansion of the universe that it has shifted from ultraviolet all the way into the infrared range, which is exactly what Webb sees. The telescope's sensitivity is extraordinary by any measure. Its instruments can detect signals from objects so distant and so dim that capturing them is essentially the optical equivalent of seeing a firefly from the distance of the moon. Alpha Centauri A, however, is not faint. It's blazingly, overwhelmingly bright, at least by Webb's standards. It's so bright that it saturates Webb's detectors almost immediately, creating what astronomers call a saturation problem. When you point an instrument designed for extreme sensitivity directly at something intensely luminous, you don't get a beautiful, sharp image. You get a smeared, bloomed mess of overexposed light that bleeds across the sensor and drowns out any fine detail near the star, including, crucially, any planets that might be orbiting it. This is why Webb wasn't initially designed as a tool for directly imaging planets around Alpha Centauri. The contrast problem is immense. A planet like Earth, if it orbited Alpha Centauri A, would be roughly 10 billion times fainter than the star itself in visible light. Even in infrared, where planets glow with their own heat and the contrast is somewhat more manageable, you're still dealing with differences in brightness that strain the limits of what any existing instrument can handle. So, the teams working on Alpha Centauri observations had to be creative. They used coronagraphic techniques, specialized masks within Webb's instruments that physically block the light from the central star, creating an artificial eclipse that allows the much fainter regions around the star to become visible. They combined multiple exposures with careful image processing. They leveraged Webb's mid-infrared instrument, known as MIRI, which operates at wavelengths where the thermal glow of warm planets is somewhat brighter relative to their host stars than it would be in visible light. And here's where something unexpected began to emerge. When you block out the blinding light of Alpha Centauri A and carefully examine the regions around it, the zones where planets might orbit, the images that come back are not clean, empty space. There is structure there, faint, complex thermal structure that doesn't immediately resolve into any simple, obvious explanation. Some of it could be the telescope's own optical artifacts. Webb produces characteristic diffraction patterns, those famous six-pointed spikes you see in every Webb image of bright stars, and untangling the real astrophysical signal from the instrumental signature is painstaking, time-consuming work. But some of what astronomers are seeing in this data appears to persist across multiple observations, multiple processing methods, and multiple teams working independently. It might be dust, it might be previously undetected small bodies, a debris disk, perhaps, like the asteroid belt or Kuiper belt in our own solar system. It might be the thermal glow of something more structured. And in the fringes of this conversation, in the preprint papers and conference presentations, and careful, hedged scientific language that researchers use when they're genuinely uncertain, there are suggestions that some of what Webb is seeing near Alpha Centauri could be consistent with the presence of planets we haven't confirmed before. This is not a press release announcement. This is science in progress, messy, uncertain, contested, and alive. Let's be precise here, because precision matters in this story. The word discovery in science has a specific meaning. It means something has been confirmed with high statistical confidence, replicated by independent teams, and survived the process of peer review. By that rigorous definition, Webb has not yet announced a confirmed, peer-reviewed discovery of new planets in the Alpha Centauri system. But science also has a phase that comes before discovery. It's called observation. It's the raw encounter with data that doesn't quite match the models. It's the moment when someone looks at a readout and says, quietly, to no one in particular, "That's strange." And in the Alpha Centauri data from Webb, there have been several of those moments. The first involves what astronomers call excess emission in the mid-infrared. When you model how bright a star should look at various wavelengths of infrared light based on its temperature and composition, you get a predicted spectrum, a kind of thermal fingerprint. If there is extra emission, more infrared light than the model predicts, it means there's something else there producing heat, something warm that the model didn't account for. Around Alpha Centauri A, Webb's MIRI instrument detected what appears to be excess emission in specific wavelength ranges. The excess is real in the sense that it survives basic data processing. What it actually represents is the subject of ongoing analysis. The most conservative explanation is circumstellar dust, tiny particles of rock and ice orbiting the star that absorb its light and re-radiate it as heat. This is not unusual. Our own solar system has significant amounts of dust, concentrated in the asteroid belt and the Kuiper belt, and this dust is detectable from afar as excess infrared emission. But here is where the story gets more layered. The spatial distribution of the excess emission, where it appears in the images around the star, doesn't perfectly match what a simple, smooth dust disk would produce. There appears to be structure in it. Clumping, asymmetry. Regions where the emission is stronger than other regions. Structure in a debris disk is significant. It's the kind of thing that planets create. When a planet orbits within a disk of dust and small bodies, its gravity sculpts the disk, sweeping clean lanes through it, compressing material into rings, creating gaps and concentrations that betray the planet's presence even when the planet itself is too faint to see directly. This is how astronomers first suspected the existence of Neptune before it was directly observed, by noting the gravitational perturbations it was causing in the orbits of other known bodies. Could the structure in the Alpha Centauri A disk be carved by a planet? Possibly. The models are being run right now in university offices and research institutes around the world, attempting to reproduce the observed structure with simulated planetary configurations. Some of those models require a planet. Some can reproduce the structure with other mechanisms. The science is genuinely unresolved. Then there's Proxima Centauri, the small red dwarf companion star. Webb observed it as part of the same campaign, and here too, the data returned something that the scientists didn't entirely predict. Proxima is a known flare star. It erupts regularly with bursts of radiation, and Webb captured several of these flare events in unprecedented detail. The spectral resolution of Webb's instruments allowed researchers to analyze the composition and energy of the flares with far greater precision than any previous telescope. What they found is that the flares from Proxima are even more chemically complex than models had predicted. The radiation profiles show signatures of specific elements being excited in the stellar atmosphere, signatures that have implications for how those flares interact with the atmosphere of Proxima b, if that planet has one. The picture that emerges is more nuanced than a simple binary of habitable or not habitable. The chemistry of Proxima's flares, as revealed by Webb, is harsh, but not uniformly so. There are wavelength ranges where the radiation is more damaging and others where it's less. The interaction between a flare star and a nearby planet's atmosphere is a dance, not a hammer strike, and Webb is giving us our first real look at the choreography. Let's say the dust disk around Alpha Centauri A is real. Let's say the structure in it eventually, under the weight of modeling and analysis, requires a planetary explanation. What does that mean for life? First, some calibration. A warm, rocky planet in the right orbital zone is a necessary condition for life as we know it, but not a sufficient one. You also need water, probably. You need atmospheric pressure. You need some form of chemistry capable of driving the enormously complex processes that living systems depend on. You need stability, billions of years of it, so that life has time to emerge and evolve past the single-celled stage. These are not guaranteed just because a planet exists in the right zone. But here's the thing about Alpha Centauri A specifically. It's a G-type star, almost identical in mass, temperature, and luminosity to our own Sunday. The habitable zone around it, the range of orbital distances where liquid water could persist on a planetary surface, is located at roughly the same distances as Earth's orbit around our Sunday. If there is a planet in that zone, it would be experiencing a stellar environment that is, in a broad sense, remarkably similar to the one that produced us. That's not a guarantee of life, but it is an argument that Alpha Centauri A represents one of the most Earth-like stellar environments accessible to our study. If we're going to look for life around Sun-like stars, this is the one we can actually examine in detail. This is the test case. The Proxima b situation is more complicated and in many ways more philosophically interesting. Because Proxima b orbits a very different kind of star, a dim, magnetically volatile red dwarf, any life that might exist there would have had to solve a very different set of problems than life on Earth. The radiation environment is harsher. The stellar wind is stronger. The planet is likely tidally locked, the same face always pointing toward the star, the other always in permanent darkness, creating a wildly asymmetric climate compared to anything in our experience. But here's what Webb's detailed flare data is beginning to suggest, that the question of habitability around red dwarfs is not as simple as too much radiation, therefore no life. Some researchers argue that life on a tidally locked planet with periodic flare exposure might actually have evolutionary pathways open to it that are simply absent on worlds like Earth. Radiation can be destructive, but it can also drive chemical reactions. It can generate free energy in a system. It can create selective pressures that push evolution in novel directions. We don't know. We genuinely, honestly, humbly don't know. But Webb is beginning to give us the data we would need to start knowing. And that is, regardless of what the answer turns out to be, one of the most significant things that has happened in the history of our species' engagement with the question of life in the universe. There's a subtler point hiding inside all of this that deserves to be pulled out and examined, because it reframes the whole conversation in a way that most coverage misses. When we ask, is there life in the Alpha Centauri system, we tend to picture it as a binary question, yes or no, alive or dead, inhabited or empty. But the scientists who study astrobiology professionally don't think in binaries. They think in gradients and timescales and chemical preconditions. The question Webb is actually helping us answer is not, is there life there right now? It's something more foundational. Has this system ever had the conditions that life requires? Those are very different questions, and the second one is far more tractable with the instruments we currently possess. A world that had liquid water for 1 billion years, even if it's now dry and barren, would leave chemical signatures in its geological record. A planet that once had a nitrogen-oxygen atmosphere might still have trace remnants of that chemistry. The history of habitability is written in molecules, and molecules are exactly what Webb's spectrographic instruments are designed to read. This is why the atmospheric characterization work that Webb is doing around nearby systems matters so profoundly. Even if Proxima b turns out to be airless today, understanding the chemistry of Proxima's flares tells us something about what that planet's atmospheric history might have looked like. It tells us whether the building blocks were ever present. And that knowledge, the knowledge of whether our nearest neighbor has ever been, at any point in its billions of years of existence, a place where the chemistry of life could have taken hold, is knowledge that no previous generation of humans has had any hope of obtaining. Webb is making it possible for the first time. Science is not a story about heroes discovering things. It's a process, and a large part of that process is systematically attempting to explain observations in the most boring, mundane way possible before entertaining exciting interpretations. This is not pessimism. It is the mechanism by which science protects itself from wishful thinking and cognitive bias. And when it comes to the Alpha Centauri data from Webb, there are plenty of scientists who are, quite rightly, pumping the brakes. The excess infrared emission could be dust, plain, uninteresting dust distributed in a simple disk that just happens to have some clumping due to local gravitational interactions, nothing requiring a planet. This would be the null hypothesis for this kind of observation. And the null hypothesis in science is always presumed true until it can be rejected with confidence. The apparent structure in the disk could be an artifact of the imaging process itself. Coronagraphy is a powerful technique, but it introduces its own complications. The process of blocking the central star and then reconstructing the surrounding region from multiple exposures involves mathematical assumptions that can, if done imperfectly, introduce apparent structure that isn't physically real. Independent teams have to reproduce the same structure from the same raw data using different processing approaches before it can be trusted. There is also the very real issue of confirmation bias. Alpha Centauri is the most exciting nearby star system we can observe. Every astronomer who works on it knows what is at stake, what a genuine detection would mean for science and for human civilization. That knowledge creates a subtle pressure, not dishonest but very human, to find the exciting interpretation rather than the boring one. Good scientists know this about themselves and work hard to counteract it, but it never fully goes away. The Proxima flare data is somewhat less contested. The observations themselves are not in serious dispute. What's debated is the interpretation. How damaging are these flares to Proxima B's potential atmosphere? Models of atmospheric erosion under flare radiation vary considerably depending on the assumptions you build into them. Some models suggest that even intense flare activity wouldn't strip a dense enough atmosphere over geological timescales. Others suggest that a planet as close as Proxima b would lose its atmosphere within hundreds of millions of years, well before life had time to develop. The honest answer, the scientifically defensible answer, is that we don't yet know which model is right. Webb's flare data makes the models better. It constrains some parameters and rules out some extreme scenarios, but it doesn't yet definitively answer the question of Proxima b's habitability. This is where popular science communication often goes wrong. The genuine excitement of the data gets amplified by headlines, context gets compressed, caveats get dropped, and what reaches the public is something that sounds much more decisive than the actual science warrants. The real story, a story of data that is suggestive, provocative, contested, and unresolved, is actually more interesting than the simplified version. It's a story of science at work in real time, at the frontier of human knowledge. And that frontier is genuinely extraordinary, even in its ambiguity. There's a thread in this story that I haven't pulled yet, and I want to pull it now, because beyond the specific observations, the excess emission, the disk structure, the flare profiles, there is something about the Alpha Centauri system as a whole that has been quietly nagging at astronomers for years, something that Webb's observations are now forcing to the surface in new ways. Alpha Centauri A and B are, as I mentioned, similar to our own Sunday. Similar mass, similar temperature, similar age, roughly 5.5 billion years old, compared to our Sun's 4.5 billion. They've been burning for a long time, long enough certainly for planets to form, for life to emerge, for civilizations to rise and fall, if the conditions were right. Here is the thing that doesn't get said enough. At the distance of Alpha Centauri, if there were a civilization, a technological civilization, with something like our own current level of electromagnetic output, we probably wouldn't be able to detect it yet. Our SETI searches, our radio telescope surveys, are sensitive enough to detect very powerful, deliberately directed transmissions. But a civilization broadcasting the equivalent of our television and radio signals the unintentional electromagnetic leakage of a moderately advanced society would be undetectable from 4 light-years away with our current equipment. Webb is not a SETI telescope. It was not designed to look for signals from civilizations, but its sensitivity to the infrared spectrum raises an interesting, if deeply speculative, possibility. Certain industrial or technological processes waste heat from large-scale energy use, for instance, would produce infrared signatures that differ in specific ways from purely natural stellar and planetary emission. This is sometimes discussed under the heading of technosignatures, and while it's firmly in the speculative corner of astrobiology, it's not fringe science. It's a legitimate area of inquiry that NASA has formally acknowledged as worth investigating. Some researchers have quietly noted that Webb's sensitivity, combined with its infrared capabilities, makes it theoretically capable of detecting certain kinds of anomalous thermal emission that could, in principle, indicate large-scale artificial processes. The key word there is theoretically. The practical challenges are enormous. The signal would need to be extraordinarily strong. The alternative's natural explanations for unusual infrared emission are almost always more plausible than artificial ones. But here's the disorienting thing. Webb is looking at Alpha Centauri and finding thermal structure that doesn't perfectly fit simple models, and we don't yet have a definitive explanation for that structure. It's almost certainly not a technosignature. It's almost certainly dust and natural planetary dynamics. But in the honest space of scientific uncertainty, where we don't yet know exactly what we're seeing, there is a flicker of something that refuses to be entirely suppressed. It's not evidence of anything, but it's a reminder of the stakes. It's a reminder of what it would mean if we found something, and it's a reminder that the universe has no obligation to be simple. And here's something else that doesn't get discussed enough. Alpha Centauri A and B are older than our Sun by about 1 billion years. That is not a trivial difference. 1 billion years is longer than the entire span of complex animal life on Earth. It's long enough, if the conditions were right, for intelligence to have emerged and then collapsed and then emerged again. It's long enough for a civilization to have built something, broken something, learned something, and left something behind, even if that civilization no longer exists in any recognizable form. We tend to think of the search for extraterrestrial intelligence as a search for something ongoing, a civilization broadcasting signals right now, waiting for us to respond. But most of the signatures we might eventually find are more likely to be archaeological than conversational, the ruins of something, rather than the thing itself. The chemical remnants of a biology that flourished and ended, the isotopic anomalies of an industrial civilization that burned out millions of years ago. We are not just listening for neighbors. We are also, potentially, excavating a history we didn't know existed. Webb is not an archaeological tool in any direct sense, but the detailed infrared mapping it's doing of the Alpha Centauri system is exactly the kind of foundational work that would allow future, more specialized instruments to know where to look and what to look for. Every observation Webb makes is narrowing the space of unknowns, and sometimes narrowing the space of unknowns is how you stumble across something that redefines what was possible. Step back from the specific data for a moment. Step back from the excess emission and the flare profiles and the disk structure, and look at the bigger picture of what Webb's attention to Alpha Centauri represents, and what it's beginning to tell us about the neighborhood of space we inhabit. Before Webb, our understanding of the Alpha Centauri system was built primarily from radial velocity measurements, astrometry, and limited photometric data. These are all indirect methods. They measure how stars move, how their light changes, and they infer the presence of planets and other structures from those movements and changes. They're powerful, but they're constrained. They tell you that something is there without showing you what it looks like or what it's made of. Webb changes this. Not completely. Not yet. The technical challenges of directly imaging planets in the system remain formidable. But the infrared data Webb is collecting begins to paint a picture of this system in terms of its thermal architecture. Where is warm material? How is it distributed? How does the radiation environment created by the 3 stars in the system shape the regions where planets could form and survive? These questions have never been answerable with anything like the clarity that Webb is beginning to provide. And what's emerging from that data is a picture of the Alpha Centauri system as a place of unexpected complexity. It's not the clean, simple arrangement that easy models might have suggested. There's structure in the circumstellar environment. There's nuance in the radiation produced by the stars. There are features that require explanation, and those explanations are going to improve our models of planetary systems around binary and triple stars, generally not just here, but across the galaxy. This is actually one of the underappreciated contributions of observing nearby systems in detail, because the processes of planet formation, atmospheric evolution, and stellar interaction that operate around Alpha Centauri are the same processes that operate around all stars everywhere. When we build better models to explain what we see here, we're building better tools for understanding planetary systems around stars that are too far away to study with this level of precision. The knowledge propagates outward. There's also something profound about the shift in perspective that Webb is enabling. For most of human history, the stars were points of light, beautiful, fixed, remote, and ultimately unknowable in any meaningful detail. Even as astronomy advanced, Even as we measured stellar distances and compositions and learned to classify stars into spectral types and understand their life cycles, the stars remained, in an important sense, abstract. They were phenomena to be measured, not places to be understood. Webb is beginning to change that. At Alpha Centauri, Webb is not just measuring a star. It's beginning to reveal a place, a system, with geometry, with structure, with a thermal landscape, with dynamics. It's the first step toward understanding our nearest stellar neighborhood, not as a point of light, but as a location, a destination, an environment. That shift from star to place is subtle but enormously significant. It's the same cognitive shift that happened when the first close-up photographs of the moon came back from the Apollo missions, or when Voyager sent back the first detailed images of Jupiter and Saturn. We are beginning to know these nearby star systems the way we know landscapes, rather than the way we know measurements. And once you begin to know a place in that way, it becomes harder to think of it as merely an abstraction. Webb is not the last word. It's the first real chapter. And what comes after it, if funding holds and ambition sustains itself, is genuinely exciting enough to make you impatient with the present. The extremely large telescope, the ELT, is currently under construction in the Atacama Desert in Chile. Its primary mirror will be 39 meters across. 39 meters. For comparison, Webb's mirror is 6.5 meters. The ELT will be equipped with coronagraphic instruments and adaptive optics systems that could, potentially, directly image rocky planets around Alpha Centauri A and B in visible light. Not the faint thermal glow that Webb sees, but direct reflected starlight, potentially revealing the actual color and surface features of another world orbiting another sun. The projected first light for the ELT is in the late 2020s. We are not talking about science fiction. We are talking about a telescope that may be operational within years, potentially capable of returning the first direct image of a planet around Alpha Centauri. Beyond that, there are concept studies for space-based observatories specifically designed for high-contrast imaging of nearby stellar systems. The Habitable Worlds Observatory, currently in the early design phase with NASA, would be optimized for detecting and characterizing rocky planets in the habitable zones of sun-like stars. Alpha Centauri A would be one of its primary targets. And then there is Breakthrough Starshot, the proposal for laser-propelled gram-scale spacecraft that could theoretically reach Alpha Centauri in 20 years. The engineering challenges are enormous. A laser powerful enough to accelerate the spacecraft, a sail thin and reflective enough to be pushed by it, electronics miniaturized to fit in a package smaller than a postage stamp, and tough enough to survive the acceleration and the interstellar medium. But the physics is real. No known law of nature prevents it. And the funding to develop the technology has been committed. If Starshot eventually launches, and it's a very large if, contingent on decades of engineering progress and sustained investment, the first flyby data from Alpha Centauri could be in human hands within about 60 years from the launch date. People alive today might live to see it. Your children almost certainly could. What do we expect those spacecraft to find? That's the question Webb is helping us sharpen right now. Every piece of data from Webb, the disk structure, the flare profiles, the thermal excess, feeds into the models that guide where we look, what instruments we design, what we prioritize. Webb is not just doing science, it's doing reconnaissance. It's mapping the terrain for the missions that follow. But there's something else happening here that goes beyond the engineering and the science, something that's harder to quantify, but no less real. Having a destination changes you, not just as a species, but as a civilization, as a culture, as a collection of individuals who need to believe that the future is bigger than the present in order to build anything worth building. For most of human history, the idea of going to the stars was mythology. It was Icarus flying too close to the sun. It was the gods in their chariots. It was the dream that kept you warm at night, but that you'd never actually pursue. Then, in the 20th century, we went to the moon. And what that did, what it did to the culture, to the imagination, to the collective sense of what was possible, was not just scientific, it was psychological. It changed the story humanity was telling itself about itself. Alpha Centauri is beginning to do something similar in slower motion. Webb's observations are making it real in a way it has never been real before. Not a point of light in the sky, not a number in an astronomical table, a place with structure and warmth and complexity and the genuine, scientifically defensible possibility of worlds. The more real it becomes, the more it begins to function as a destination in the human imagination, a pole star for civilizational ambition, a reason to keep building better telescopes and faster spacecraft and more powerful lasers, a reason to think in centuries rather than quarters. That is not a small thing. That might, in the long run, be the most important thing. Webb's observations of Alpha Centauri produce not a data set, but a direction. Here is the thought that I keep coming back to, the one that sits quietly at the center of everything this story is actually about. When Webb looks at Alpha Centauri, it's looking at a system that is, in many ways, a mirror of our own, same kind of star. At least in the case of Alpha Centauri A, similar age, similar stellar neighborhood, and if the data is pointing where some researchers think it might be pointing, if there are planets there, potentially rocky, potentially warm, potentially sheltered by atmospheres, then we are looking at a mirror of Earth, 4 light years away. 4 light years, 4 years for light to travel. In the scale of the universe, this is nothing. In the scale of human experience, it is everything. It is a distance we cannot physically cross. It is a message we cannot send and receive on any timescale meaningful to a human life. And yet it is, by the vast and impersonal metrics of cosmic distance, almost touching distance. If there is life there, if, in this moment, as you're watching this video, something on a planet around Alpha Centauri A is alive and experiencing its world, then the light from our sun is arriving there right now. The light that left our star 4 years ago is illuminating whatever exists in that system at this moment. We are already in each other's light. We have been for all of human history. We just didn't know what that meant. And here's the part that nobody talks about enough. If there is life there, and if it developed technology, and if that technology included something like telescopes, they could already be seeing us. Not us specifically, not this video, not this moment, but the infrared signature of our planet, the faint wobble our Earth induces in the sun's motion, the slight dimming we cause as we transit across the sun's face, are all potentially detectable with an instrument something like Webb from Alpha Centauri. We are, from their perspective, in the same position that Alpha Centauri is from ours, a nearby star system with a potentially interesting planet, detectable in principle, unreachable in practice. We are each other's closest interesting neighbor, and we are both, right now, squinting at the light. That's not a discovery, that's a perspective. But sometimes perspectives change everything. Consider what it means to communicate across 4 light years. If you sent a message to Alpha Centauri today, a radio signal, a laser pulse, anything traveling at the speed of light, it would arrive there in 4.37 years. And if something there received it and responded immediately, you wouldn't hear the response for another 4.37 years, nearly 9 years for a single exchange. In the entire recorded history of human civilization, which stretches back roughly 5,000 years, you could have conducted only about 280 such exchanges. The conversation would be slower than the lifespan of individual human beings. Entire generations would live and die between question and answer. That's not a reason to despair. It's a reason to think differently about time, about continuity, about what it means to be part of something larger than a single life. The project of understanding Alpha Centauri, of sending signals, of launching probes, of waiting for data, is inherently multi-generational. It asks us to care about outcomes we won't personally witness. It asks us to plant trees whose shade we'll never sit under, to use the old expression. And yet humans have always done this. We build cathedrals that take centuries to finish. We plant forests that take generations to mature. We write books and make art and raise children in the full knowledge that the impact of those acts will outlast us by centuries. The exploration of Alpha Centauri is simply the largest version of that same impulse, the impulse to extend ourselves forward in time, to leave something for the future that the future will be grateful for. Webb is the beginning of that extended act. It is the first careful look, the first real data, the first moment where our nearest stellar neighbor begins to be known rather than merely observed. And from that beginning, if we are patient and ambitious and wise enough to keep funding the science and building the instruments and launching the missions, everything else becomes possible. Carl Sagan once described Earth as a pale blue dot, a tiny fragile mote of dust suspended in a sunbeam, the only home we've ever known. It's one of the most resonant images in the history of science communication, not because it diminishes us, but because it contextualizes us. It places us in the universe rather than at the center of it. Webb is doing something similar, but in reverse. It's not taking a picture of us from far away. It's looking out from us, toward the nearest light, and beginning to reveal that light as a place, a specific, structured, complex, potentially life-bearing place. The data from Webb's observations of Alpha Centauri is not yet a discovery. It may, after the analysis is complete and the papers are published and the community has argued it through, turn out to be relatively mundane, dust and dynamics, interesting but not paradigm-shifting. The scientific process will decide. It always does. But the act of looking, the act of turning, the most powerful telescope humanity has ever built toward its nearest stellar neighbor, and saying, in effect, "Show us what you've got." That act is not mundane. It is one of the most consequential things our civilization is doing right now. In the quiet margins of a world that tends to fill its attention with other things. Because somewhere, 4 light years away, photons are leaving those stars and traveling toward us. They take 4 years to make the journey. And when they arrive, instruments built by human hands and human minds catch them, turn them into numbers, and then, in a process that is itself a kind of miracle, those numbers become understanding. That's what we did. That's what we're doing. We built a golden eye and pointed it at the nearest star and asked it to tell us something true. And the nearest star, for the first time, began to answer. What that answer ultimately says, whether it speaks of planets or dust, of complexity or simplicity, of life or its absence, we don't yet know. But the conversation has started. And once a conversation like that starts, it doesn't stop. It just gets more interesting.